There's John Black, superchemist, going over a few equations that's for organic electrosynthesis. And I wanted everyone to know that there's only a couple more weeks and I can start up with some more experiments and, make videos. One of the first electrosynthesis things that you'll learn in chemistry is the Coulomb electrolysis. That's basically taking two carboxylic acids and you oxidize them and you get an alkane. All right, you can see up here is the formula. Basically, whatever's left, you get your CO2 there, your carboxyl group. What's left is R, and you got two of them. They link up. So this you're usually going to get an even amount or a symmetrical alkane, or an even amount of carbons, because if you have two of them, even if you have an odd number like 3, 2 times 3 is 6, it'll always come out even. So if you want to make hexane, you'd need 1, 2, 3 plus your CO2 carbon. That's 4 carbons. One will disappear, you'll be left with 3. 2 times 3 is 6, you'll make hexane. If you want octane, then you need 1, 2, 3, 4, right? Because 2 times 4 is 8, and then the CO2 disappears. Now, one great thing about this reaction is not only can you make alkanes, but you can make rings. Rings, to me, is, that's the ultimate. That's a carbon-carbon bond. Now, I want you to look at this. Look at these two. See how they have the carboxylic acid on each side, both sides. You will have an intramolecular reaction if you put DC through this, right? It's a little methanol for solvent. And keep in mind, when I have these acids, I think that you would use the salt of the acid. And it depends on the ratio of what you want to do. I'll get into that later. I'm just doing generic equations in this video. But you can see there's 5 carbons plus the 2 carbons for the carboxylic acids. They disappear, so you're left with the 5 carbons that linked up, and you got pentane. This one you have 6 carbons plus the 2. That's 8 carbons total to get cyclohexane, cyclopentane. Now for this one, you can make either acetic acid or ethyl acetate, right? You start out with ethanol, right? Do your DC. It's at the anode, so you're oxidizing it. And you can oxidize it up to acetic acid. Now, if you have acetic acid and alcohol, you can also, continue on and make, depending on your voltages and your electrodes, what type of electrodes, you can have it stop here, or you can have it continue on to make ethyl acetate. Again, you're just using electrolysis. Now, this top one, I'm unsure about this, but I think it might work. Basically, it's glycine. All these next couple examples are about amino acids, that you take if you're a bodybuilder type person. That's what proteins are made of. Proteins are chains of amino acids. This is the simplest amino acid. And all an amino acid, when they're talking about that, that just means it's a carboxylic acid with an alpha amino group. And if you take this amino group out, right, what are you left with? You're left with acetic acid, right? You got 2 carbons there, 1, 2, and they threw an amine on there, an amino group. That's it. It's acetic acid with an amino group on the alpha carbon. Alpha carbon just means it's 1 carbon over. If it was 2 carbons over, like here, 1, 2, or 1, 2. If it was on this carbon, at the very end there, that would be your beta carbon. Then keep going on, delta, gamma, etc., whatever the other ones are. But you'll notice on aniline is another amino acid, and it's just propanoic acid. 1, 2, 3 carbons, propanoic acid. Only it has an amino group on the alpha position. That's all that's all an amino acid is. So anyways, on this top one, right? Now this one has nothing to do with DC, okay? This I'm talking about a soda-lime decarboxylation, right? That's where you, like if you have sodium benzoate and you put it in with some base like sodium hydroxide, calcium oxide, and you heat it real hard with a real hot with a torch, and you'd rip off the carboxylic right here, and you'd end up with whatever was left. In this case, you know, you would be left with methylamine. Now, will this work? I don't know. It should, though, but because it's such a small molecule, I don't know. It might work differently, you know what I'm saying? But if it does, glycine, I mean, that's just an amino acid. Anyone can buy tons of that. You know, throw it in a can, the salt form of it, and put some sodium hydroxide in, some calcium oxide, heat it real hot, you know, and distill out your methylamine. You can have it distilled directly into an acid, so it would turn into the salt. You know, you'd have methylamine hydrochloride. That way it wouldn't boil away as easy. But I think that might work. You know, what do you think? Let me know what you think. And the next reaction, now this is, we're back to electrolysis. All right, most of these are electrolysis. Now, aniline, that's just propanoic acid with an alpha amino group, right? It's an amino acid. Throw some DC on it, right? And you'll do an oxidative decarboxylation. Two H's come off, and this single bond turns into a triple bond, and the carboxy group comes off. Now you have a nitrile. This is actually the smallest or simplest nitrile that you can have. It's a hydrocarbon. You know what I mean? It's not a salt like potassium cyanide. This is hydrocarbon nitrile or cyanide. Now, what good is that? Well, you can take that and do this. It's called the Stevin aldehyde synthesis. You take your nitrile, and I think it's called acetonitrile, some hydrochloric acid, stannous chloride, and I'm guessing you would reflux it. I don't really know. Because I'm just going over a generic thing here. You make your imine. The imine reacts with the water and makes it into an aldehyde. So you can make acetoaldehyde. I call it ethanol. From aniline, which is just a amino acid that anyone can buy. Does it work? I mean, all these work. It's just, can you get them to work, you know, without using some weird thing like putting it under pressure or doing this or that. But, you know, you need some kind of weird machinery or something, you know. Maybe, I mean, this definitely works, right, to make this. And this reaction works too. I just don't know how. It definitely, because it has a name to it, so it works, obviously. Okay, now we're up to isoleucine, okay. And that's another amino acid. You can see it's just 1, 2, 3, 4, 5. That'd be pentanoic acid with a methyl group on the here and an amino group on the alpha position. Now again, this is not electrolysis. I'm saying, what if you did the soda-lime decarboxylation with this? Okay, threw it in with some, you know, took the salt form of it, threw some sodium hydroxide, some calcium oxide, heated it up real hard, real hot, and distill out this, which would be like 1, 2, 3, 4, which would be like butylamine. Okay, only it has a little methyl group on here, so it'd be 1, 2, 3. It'd be 3 methyl butylamine. So if you want a high boiling primary amine, that would be a way you could go. Another way, okay, is down here. We're back to the electrolysis, right? Same starting material, isoleucine, right? Amino acid anyone can get. You're going to oxidize it to a nitrile, right? Just like up here, where I said the propanoic acid, the aniline one, you'd take it and make it into a nitrile, right? You take off the carboxy group and you change this amino acid into a nitrile. So same down here. You're going to take off the carboxy group, change the amino group into a nitrile, see? And you might say, well, what good is that? Well, you just oxidized it. Now you can take it and put it back into another DC electrolysis machine, but this time, right, you're going to put it on the reduction side of the electrolysis apparatus, right? Because you want to reduce this nitrile into an amino group. And again, you end up with the same thing. 3-methyl butylamine, right? And you use DC for the whole time. All right, now look at this. You have a nitropropene, right? That means you have a double bond with a nitro group. You can put that into an electrolysis apparatus. Use some DC. It's at the cathode, so you're reducing, and you can turn it into an oxime. I don't know if you can see that. See how it's a double bond to the N, and then the N has an OH instead of, an H like an amine. It's an oxime. And you can do a lot of stuff with an oxime, right? But another thing you can do is you can take your nitroalkene and you can use higher voltage, okay? Everything's pretty much the same, but instead of making an oxime, you're going to make an amine, okay? And in both cases, you'll notice you're taking out the double bond, right? You're taking out the double bond and making it into a single bond. You're taking off the oxygens off of the nitrogen group and you're putting hydrogens. On this one, you're making your oxime. But in both cases, you're making a single bond. My whole question here to that is, because so far, all these reactions I've mentioned are, they're known reactions or whatever. But what about this now? What if I just have an alkene with no nitro group? Can I use electrolysis to make it into an alkane, a single bond? The same with the nitro group. Let's say I have methyl nitromethane. Can I, without a double bond, put it into an electrolysis apparatus and make methylamine? Because that's what you do up here. You reduced it up here. Same way with a double bond, you reduced it up here. So, is that possible? I mean, I'm not talking about double bonds in a benzene ring. That's hard. Although you can. Here's an example where you do take out one of the double bonds. And you can see here it's a single bond now. If you have certain things connected to the group, to the ring, then yes, you can take out, this is kind of like a Birch reaction or reduction. You're taking out just one double bond out of the ring. That's it. I just wanted to show you a few ways that you could, electrolysis, or at least organic electrosynthesis, you can make a lot more things than you would think. You don't have to just make chlorine or make, copper or something like that. You can make alkanes, amines, oximes, anything you can think of, you can do with an electrolysis apparatus. So anyways, I'm running out of time. Seems I'll have a great day, and always remember, science is great.